thinning out. But we will start anyway. Maybe everybody thought this lecture would be depressing because it's about limitations of computing. OK, so there are three kinds of things that I'm going to talk about today. The first one is theoretical limits on computing, and then practical limitations on computing, and then the limitations that have to do with people rather than only with computers. So starting with things that are theoretically impossible. This is called the halting problem. And it's the most famous of the things that can't possibly be done by a computer. And the impossibility of the halting problem was proved by Alan Turing, whose name you've heard before. He's the guy who single-handedly won World War II. But in his spare time, he also developed a theory about the capabilities of computers. And he did so, by the way, at a time when there really were hardly any computers. So he did it sort of in the abstract as a mathematical exercise that turned out to be very, very important. So let's take a look here. You see that? Yeah, I think so. But let's make the stage smaller for a moment. So I have this block called weird. And here's what weird does. Oh, I guess I made this a long time ago before there was a report. Here, let's fix it. So what this really means to say is this. OK. So here we have a block, this weird block, that if its input is 7, it reports weird 7. So does that ever finish? No. Right? It keeps calling itself with the same input over and over again forever. If the input is anything other than 7, then it just reports its input without any recursion at all. So you and I can look at this and say, well, this block will halt for any input other than 7, but it won't finish for an input 7. So how does my little block do? So if I say, does the weird block with input 5 ever finish? It says true. 7. False. Pretty good. 23. True. And so on. So that's what we want, except we want it to work for every possible function, like weird, in anything that takes an input, and also work for any possible input value. So let's take a look at how I implemented this does it finish block. OK, why isn't this working? Thank you. And of course, I cheated. I just report input is not equal to 7. So this does it ever finish block works great for the case of weird. But what we want is one that works in general. And the question is whether we can achieve that. And to show that we can't, Turing created this block. So try takes a function as input, and it says, if the try block with input function ever finishes, so it's asking about itself with this input. And if the does with input ever finish block says, yes, you are going to finish with input fun for function, then loop forever. So if the does with input ever finish block says, yes, you do finish, make sure I don't finish. If the does with input ever finish block says, no, I don't finish, then we don't do this forever, and we report true. So this try block is arranged to turn whatever our does with input ever finish block says into a lie. Okay, so this is a kind of perverse function whose entire purpose is to make sure that no matter how you write the does with input ever finish block, it can't possibly give the right answer. Because if it says yes, we make sure the right answer is no. If it says no, we make sure the right answer is yes. Okay? So no matter what does input ever finish, does with input ever finish says, it can't be right for this particular case. So that proves that we can't do it in general. Now, it could have turned out to be true that only this one screwy case fails, and otherwise we can do it. But that's not the case. It will fail in lots of cases. There are many functions we can construct that would have this behavior. As far as sort of real useful programs are concerned, the state of affairs is that we can solve this problem some of the time for interesting special cases. So in other words, we can write a does this ever finish function that will say no correctly in many useful situations. So it will catch some cases of a program that runs forever, but it can't catch all of them. So more generally, we can't write a program that says, here, find the bugs in my program, and tells you what the bugs in your program are. So it's a nice thing that we would have liked to be able to do, right? Have something that automatically does your debugging for you, but we can't. Okay, questions about that? Yes? All right, here's a good clicker question. Who understands what the problem is with does and try? Yes, who's got that? Thumb up, yeah, thumb up, thumb down. Okay, I'm seeing more, some of each, but more downs than ups. So let me try again. Yeah, well, let's first just look at this block without an input in it. So this is the goal. This is the thing that we're trying to invent. And we'd like it to work for functions of one input. That's just sort of a simple special case to think about. So the first input here is a function of one input, any function of one input that you might have written or whatever. And then we say what the input to your function should be. And this is a predicate block. It's a hexagon, which means it's supposed to return true or false. Okay? Namely, it should return true if this function actually works, computes an answer for the given input. And it should return false if this function with this input runs forever. Okay. Thumbs up, down. Who understands what the goal is? Great. Okay. Now, I showed you an example that only works for one function. Let me put that back up again for a second. So here's, does this function with this input ever finish? And it works for the function weird, because if the input is 7, this is going to report false. If the input isn't 7, this is going to report true. And we know by looking at the weird block that I wrote before that that does correctly describe the behavior. So this is a cheating solution to the problem because it only works for the one function that I had written. Okay? But Turing is saying, I want to prove that this is not possible in general. Now, maybe this is the stumbling block for people. When you want to prove that something is possible, you can straightforwardly do that by doing whatever it is, right? So I want to prove that it is possible to write a factorial function. So I go ahead and write a factorial function. And I say, here it is, see? And we run it a few times, and it gets the right answer. And we can mathematically analyze it and show that it gets the right answer, and then we're done. So proving that something is possible is at least sometimes straightforward. Proving that something isn't possible is harder. Because, maybe next year they'll invent some whole new kind of computer, a quantum computer or something, right, that works in a different way. And, how can I show that no matter what technology they develop, it's never going to work? Well, the way we do that is a proof by contradiction. So I start by saying, let's pretend I've written this function. Okay, not the cheating one that I wrote, but the general function that takes any function and any input and gives me a true or false. Okay? Oh, and by the way, this function itself can't run forever. This has to guarantee to come up with an answer in finite time. Okay? So I don't know how to write this, but let's assume that Dan has written it and he hands it to me. So I make up this function try, and I say, look, Dan, your block can't possibly work because, in general, it might work for some cases, but it can't work in all cases because here's a case that it has to fail in. Okay? And the trick is that my block try, in general, this thing could take any kind of input. The function, like it could be a function of a number, as it was in the case of weird. But my function try is a function of functions. And because it's a function of functions, I can use myself as an input to it. And that, that's useful here. But, okay. Oh, in fact, that's what I meant to do. There, that's what I meant. So since you claim, Dan, that you can always tell whether I'm going to finish a computation, I'm going to ask you whether this function itself will finish if I give it this function itself as an argument. Okay? So, that's a perfectly good question. Your block should report true or false. You're going to tell me true if this computation finishes. You're going to tell me false if this computation runs forever. So what I do is, if you tell me true, I run forever. Okay? You told me I was going to finish in a finite amount of time, and I make a liar out of you by running forever. On the other hand, if you say false, if you tell me that I'm going to run forever, I just report true right away. I don't run forever. All right? So I've carefully constructed this function so that no matter what Dan's block says about it, it's got to be wrong. Thumbs up or down? You with me? Okay, great. Isn't that a clever idea? Imagine yourself at a time before there really were any computers, figuring out about how computers are going to work when they invent them, and coming up with this sort of proof. It's really brilliant. Okay. So that's one example of an uncomputable function, the first of many. There are several more particular functions that we know about that are uncomputable. So another example is Let's see, how do I put this in non-technical language? What's the biggest number that a computer can compute with a program that's only a certain size? For size n, what's the biggest number that that program can compute? And that turns out to be an uncomputable function. That's less interesting than the halting problem one, but it's just to show that there is another one. And in fact, it's going to turn out that almost all functions can't be computed. The functions that can be computed by a computer are a tiny little sliver of all the functions that there are. And not to mislead you about that, both of those answers are infinite. So the number of functions is infinite. The number of computable functions is infinite. But it turns out that there are different levels of infinity. And the infinity that's the number of computer programs we can write is way, way smaller than the infinity that's the number of possible functions. So that's for what it's worth. In fact, most functions we can't even describe. Most functions I can't even sort of explain to you what the function would be. OK. Moving on to the next question. I have a program. Oh, actually, I should go back to this screen because I have to show you my Fibonacci program. Here it is. It says fib of n, if n is less than 2, report n. So fib of 0 is 0, fib of 1 is 1. Otherwise, report the n minus 1th Fibonacci number plus the n minus 2nd Fibonacci number. Right? So that you understand the definition of Fibonacci numbers, right? Each one is the sum of the two before it. So you have 0, 1, 1, 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, and so on. Okay, that's the Fibonacci numbers. This program directly reflects that definition. And the question is, how long will it take to compute Fibonacci numbers? So I click the button. For fib of 5, I get an answer basically instantly. What if I take fib of 10? You think we're going to be able to see how long it takes, or will it be basically instantly like before? See how long, basically, yeah. See how long, because it'll be slow, or basically instantly it'll be fast. Some of each. You think, okay, let's take a look. Here's fib of 10. Oh, that took a little while. Not too long, but a little while. How about fib of 15? Wake me up when it's over. Right? Yeah. Sorry? Oh, you're right. It's not Alonzo. Oh my gosh, this is such an old project. It has the old Gobo in it. You're absolutely right. So that took quite a while. How about fib 20? You think we should try fib 20? Who wants to try fib 20? Who doesn't want to try fib 20? Yeah, good call. This procedure takes an amount of time that's an exponential function of the number we're taking a Fibonacci of. It's like 2 to the nth power. It actually isn't 2 to the nth. It's 1.57 something to the nth, I think, phi. Is that right? But it's something to the nth power. And so basically, every time we add 1 to the input, the amount of time doubles, roughly speaking, or 1.5. 1.6, okay. So almost doubles. Now, Fibonacci is a really simple function, and it's possible to write a program to compute it that is fast. So in this particular example, I could change the way I wrote the program so that it would essentially take linear time. So every time we double the number, it would double how long the program takes. And that would be great. We could get up to fib of several thousand without you being able to tell the amount of time it's in the blink of an eye. But doing it this way, where each call to fib causes 2 recursive calls to fib. So that's the problem. If I do fib of 15, that asks for fib of 14 and fib of 13. Now fib of 14 asks for 13 and 12. 13 asks for 12 and 11. So next level down, there are 4 recursive calls, 8 recursive calls. We should have more and more recursive calls until we get down to where n is equal to 0 or 1. So that's what makes it take such a long time. This problem, as I said, we could be cleverer about how to write the program so that it wouldn't take this long. But there are problems for which the solution has to take exponential time. And there also are problems, a very interesting class of problems, for which, as far as we know, the solution takes exponential time. So an example of the first one, a program that has to take exponential time. I give you a set of things like x, y, z, and I want you to make all the subsets. So I gave you x, y, z. That's a set. I want x and y and z and xy and xz and yz. And let's not forget the empty set and the set we started with are also subsets. So 3 elements in the original set, 1, 2, 3, 4, 5, 6, 7, 8 subsets. In general, if you have n elements in the set, there are 2 to the n subsets. And the reason for that is each element can either be in the subset or not be in the subset. So that's n yes or no decisions we have to make. So there's 2 to the n ways that we can make all those decisions. You can say yes, 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 or yes, yes, no, or yes, no, yes, and so on. Sorry? Like the light switch, yeah. Like those light switches. Yeah, there you go. There are 8 different arrangements of those light switches we could have. So since the answer to the problem has 2 to the n pieces, it has to take at least 2 to the n time to list all of them, right? No matter how clever we get, just the printing out of the answer is going to take 2 to the n time. So that's a problem that definitely has exponential solution. The problems that maybe have exponential time solutions are a very interesting class of problems called NP, which stands for non-deterministic polynomial, for which the following is true. Suppose somebody hands you a purported solution, says this is the answer to the problem. You can check whether that's true quickly. But if somebody doesn't hand you a solution and you have to compute it yourself, you have to basically try all the possibilities, and that's going to take exponential time. Now, those problems, so an example, a very important example of a problem like that is breaking somebody's password, right? Because if I tell you my password, you can, try logging in as me and see if it works quickly. But if you have to try every possible password, the number of passwords you have to try is an exponential function of the number of letters in my password, right? There are other examples. You may have heard of the traveling salesperson problem, which has to do with, let's say you travel around selling stuff and you have to go to every state capital. And the question is, what order should you drive around in to minimize the amount of time you spend on the road? And for every pair of state capitals, we know how long it takes to drive from this one to that one. So there is an answer. There is a shortest possible route. And finding out what it is takes exponential time. So exponential time, in the example that we saw with the Fibonacci numbers, for n equals 15, it was already pretty slow. For n equals 16, it's twice as slow. How slow is it going to be for n equals 100? Well, 2 to the 100th power, right? Whatever that is, times the slow, basically. That's a big number. So for practical sized problems, like all the state capitals, n equals 50. Unsolvable. 2 to the 50th power is like way too many for us to be able to solve that problem on today's computers or tomorrow's computers. See, problems that take linear time, you know, if n equals a billion or something, like your Google and you're looking at everything on the web, maybe solving your problem is pretty slow, but next year the computers are going to be twice as fast and you can probably handle it. But for exponential problems, when the computers get twice as fast, that only gives you an increment of 1 in how big a problem you can solve. Right? So those problems are called intractable, meaning it's theoretically possible to solve them, but in practical terms, we're all going to be dead before the solution would come out. So that kind of intractability can be addressed to some extent with parallelism. You know, if you have 1,000 computers at once, that gives you, you know, a pretty big increase in how big a problem you can solve. If you have lots of computers, if you're a SETI at home, right, and you have millions of computers working on the problem, then you can really make a dent in even very big problems. So there's this thing called quantum computing that kind of lets one computer pretend to be a lot of computers in parallel, using mechanisms that I'm certainly not going to tell you about because I don't know anything about it. But we do know something about the theory of quantum computers. And one of the things that we know, sadly, is that these NP problems, the ones that if I give you an answer, you can check it quickly, but you can't find the answer quickly, are not, or at least not all, going to be solved by quantum computing. Some things are still going to be slow, even with quantum computers. Now, it may be, for all we know now, it may be that somebody's going to invent a cleverer algorithm, the same way I could invent a cleverer version of the Fibonacci program, right? And we know how to do that for the Fibonacci problem. We don't know how to do it for things like traveling salesperson, but it's theoretically possible that one of you is going to invent an extremely clever algorithm for these NP problems. And if you do, or if you prove that it can't be done the way Turing proved that you can't solve the halting problem. So if you prove that these NP problems can't be solved in a short amount of time, you win $1 million. There's a prize out for solving this problem, the so-called P equals NP problem. If your solution is that you can do it, you actually win a lot more than $1 million because you patent your solution and lots of companies pay you a lot of money to be able to use it, because the NP problems include a lot of important scheduling problems. Like, let's say you're FedEx or the post office, and you have a fleet of trucks that are going to drive around delivering things to people. And you'd like to use their time efficiently so that your drivers kind of, you know, stay in one place for a while and then move to the next place and so on, and do that in all the right order. That's an NP problem. So FedEx will pay you a lot of money for your invention if you invent this. Everybody is betting that it can't be done. partly because, a lot of smart people have been working on this for a long time without finding one. And also partly because one of the NP problems is generating proofs of theorems. So if you can come up with a fast solution to NP problems, then all the mathematicians are out of business because your program will sit there churning out proofs of mathematical theorems quickly. So for that reason, too, everybody's betting that it can't be done. Okay. That's the end of the technical part of limitations of computing. And the last little bit of time, I want to talk about the human problems that get in the way of computing. And let me put that first slide back up, actually. So 2 pieces. One is people make mistakes. And remember, because of the halting problem, we can't catch those mistakes in an automated way. Or rather, in some cases we can, but in some cases we can't. Oh, you want me to turn my phone off? All right. Just move my phone away. Does that help? Ah, much better. Okay. I hate technology. Okay. Yeah, see, people make mistakes. Did I tell you about the Therac 25? And we talked about risks of computing. This is a, what? Yeah. The X-ray machine? Yeah. Right. So that was a famous example of people making mistakes. And let me just remind you, it taken quite a while to catch all of them. So the sequence of events was people started dying. The company looked at their code and found a bug and fixed it and said, we've solved the problem. And then some more people started dying and so on. So it took a lot of that to get it right. So some of the limitations of computing have to do with it just being hard to get things right. It's hard to get user interfaces right. So who hates bspace besides me? Yeah. Why do you hate bspace? Yep. So the user interface is terrible. It takes too many clicks to get to anything, and each click takes an hour and a half for the next screen to come up. And the things are named and organized in such a way that it's hard to know which of those things down the left column you have to click on to find the thing you're looking for. Terrible user interface. So that's an example, not of the limitations of computers per se, but the people who programmed bspace just didn't do a very good job. In principle, they could do better. Sorry? Yeah. Yeah. Yes, that's right. It's because they didn't hire a student to write it. They hired a professional outside company, basically. Is it? Sakai, all right, okay. Oh, really? All right. Well, then I don't know why. I don't know why it isn't better. Okay, I do know why. Here's why. It's because the people who are affected by the badness are not decision makers and not taken seriously by decision makers. So the people who chose to set up bspace, they don't use it very much. Not the way students do. So that's why it's bad. There ought to be a rule that people have to use their own software, But the other answer, too, is that, really a lot of software is really bad. And it's because it's hard. It's hard to catch everything, find all the mistakes, find all the inefficiencies. So I have no idea why it's so slow when you click on something to get to the next screen. Other people do better than that. But yeah, user interface is hard to get right. A lot of things are hard to get right. So that's a limitation of computing. The computing that we get is only as good as the programming that we do. And you're right, we teach computer science and we try hard. It isn't Berkeley people who wrote the software though, so somebody else is at fault. But it could be Berkeley people who write the software. So feel free to get a job over at educational technology and improve the B-Space software. Anyway.
They are receptive to input. So I've had some people send me
Yeah.
They say, we'll queue it up, and then one or two of them has actually gotten fixed.
Okay. Sometimes they fix things. If you have a very specific, this one thing is bad, they can sometimes fix it. But, it's slow as molasses. I've said that to them repeatedly. They say, oh, we don't have that problem. So I don't know. Maybe if you're right near the server, it works better. Yeah, there you go. Rewrite B-Space. Yeah. So that's a limitation of computers. Sometimes people do a good job. I mean, there is good software in the world. But it takes a huge, huge effort to do it. The other problem on the slide here is about people being greedy. So we've talked some about, for instance, the privacy problems in Facebook. That's not because of mistakes. That's all deliberate. It is. That's how Facebook makes their money, is by selling information about you to advertisers. The good news is not everybody is greedy. So, some stuff that's out there in the world is free and doesn't try to hurt you in some way. But some things do. Sometimes the whole purpose is to control you in some way. Sometimes there's another purpose. I mean, Facebook, you guys use Facebook because it's useful to you. It serves purposes other than just making money for the Facebook company. But one of its purposes is to make money for them, and that fact affects the way the software works. Sometimes these two things interact. So there'll be a mistake in some software, and the company will try to hide the fact instead of trying to fix it. Or maybe they'll try to fix it also, but meanwhile they'll deny that there is a problem until they have a fix ready. So, Toyota is sort of in trouble for that about their cruise controls. The most famous example wasn't a software example, it was about hardware, namely the Ford Pinto. That was the one that if you rear-ended the Pinto, the gas tank would blow up. And Ford engineers knew about that, but the Ford management decided not to recall the cars and fix it, but to wait until some people died, which happened. So that's just greed, and that's a limitation of computing too. And that's basically all I have to say, so questions? Doesn't have to be questions about greediness, anything. Yeah? What's wrong with Toyota's cruise control? Every once in a while, a Toyota car suddenly starts accelerating out of control. Yeah. 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 Toyota's response to this problem was first to deny it, to say, well, you know, you meant to push the brake, but you actually pushed the gas. It's your fault. And their second response was to say, oh, the gas pedal got caught underneath the carpeting and was just mechanically wedged down to the floor. But people who, you know, were pushing the right pedal and didn't have that kind of carpeting still have had the problem. So it's not absolutely clear that it's a cruise control. I mean, nobody's found a bug in the cruise control software. People have managed to make it fail under test conditions. Toyota says that those test conditions are unrealistic. The way they tested it does not reflect how people really drive. But the other thing is that whatever the source of the problem, there's a known workaround for it, which is you can program your cars so that if the driver is pushing both the brake and the gas pedal at the same time, you believe the brake. Okay? That would be safer. That would, you know, fix this problem, even without finding the original cause of it. Why don't they do that? Because if you happen to be a race car driver, there are times when you actually do want to push both pedals at once, having to do with getting around curves in the absolutely least possible amount of time. Don't ask me why. It doesn't make sense to me, but that's what I've read. And so that's why, you know, so as to be able to show how fast their cars are in competition, they don't want to believe the brake over the gas. It's only on manual transmission? Oh, that it's useful, you mean? Yeah, okay. Yeah, so it's really stupid of them, but that's how it is. Yeah.
I read some cool stuff that's happening with Connect, started by Microsoft. Now people are programming it to be used on computers. And is Berkeley doing anything in that space right now?
The BitLab actually bought one last week.
Oh, really?
And yeah, we have a couple people who are experimenting with user interfaces and stuff for it.
There you go.
Names after it's pretty cool though.
Oh yeah, the question was, is Berkeley doing anything with Microsoft Connect? And the answer is yes. The Berkeley Institute for Design, which is one of our research groups, is working on that stuff. So.
The Connect is a depth camera, for those of you who don't know. It's the first one, I think before, a couple weeks ago, you could only get one for about $4,000, but then Microsoft released one for $150.
Okay, so it's something that can detect where your body is without you needing to carry a controller.
Right.
So you can play games untethered. Yeah. Any other questions on limitations of computing? Going once, going twice? Okay, see you Wednesday.